Hello, everyone. Welcome to another NL seminar. And today it is our great pleasure to have Feng as our guest speaker. Feng is a postdoc at the University of Chicago, working with Shenhao Dan. He got his PhD from the University of Maryland under Jordan Boyd Graber. He is interested in human-AI cooperation. In other words, how machine learning can help humans make better decisions and how humans can provide supervision more effectively. His past work focuses on natural language processing and covers topics including interpretability, adversarial attacks, robustness, and human-in-the-loop evaluations. Today, he will give a presentation on pragmatic interpretability. As a reminder, there will be a QA session at the end of the talk, but if you have any questions, feel free to ask them throughout the talk. And as usual, please keep muting your mics unless if you have a question or comment to ensure the clarity of the talk. Without further ado, please join me in welcoming Feng, and I hope you enjoy his talk.
You can see
can you see the slides?
Well, we see your presentation notes.
Okay. Do you now see like the correct window?
Now it looks good.
All right, sounds good. All right, thank you so much for having me. I'm very happy to be here to talk about some recent work on interpretability. Please interrupt at any time for questions. I would very much like this to be interactive. So as a motivation, let's consider an oversimplified taxonomy of tasks that humans and AIs can do. Let this green circle represent tasks that humans can do, and this red circle represent tasks that AIs can do. In recent years, we've made a lot of progress at growing this red circle, often under the slogan of narrowing the gap between human and machine intelligence. And machine learning models are quite successful at emulating human intelligence on these tasks, even ones that are considered difficult. But I would argue that there's also this green circle that represents tasks that humans cannot do themselves, but can do with AI assistance. So in this red circle, the paradigm can be described as automating human intelligence, whereas in this green paradigm, you can describe it as augmenting human intelligence. Of course, one challenge to both paradigm is the interpretability of machine learning models in general. Under the automating paradigm, we see AIs covering more and more grounds in terms of doing tasks that humans can do. But when we make those claims, we are mostly looking at simple metrics like accuracy, precision, recall. But there are other dimensions to measuring human intelligence that these simple metrics cannot cover. And once we start looking at these dimensions with more elaborate evaluations, we see a lot of counterintuitive behaviors. So a lot of my earlier work is devoted to an adversarial approach and trying to figure out how the models can behave badly and how that can hinder the collaboration between humans and AIs. Next, I'll briefly highlight some of those counterintuitive behaviors that we've identified. The first one is called trigger. So with like normal input, you get normal output from the model. Trigger is a prefix that you append to the input that causes the model to do like weird things. So intuitively, you can think of trigger as kind of flipping a switch in the model and put the model into some weird mode. An example would be for a sentiment classifier. There's this trigger that we found called zoning tapping finesse. It's nonsensical because it was discovered algorithmically. But if you prepend this trigger to positive reviews, almost all like SST model will give you negative classification. Similarly, for GPT-3, there's this kind of like racist trigger that you can prepend to a neutral context, and it is highly likely that the model will spit out something that's offensive. So I'll show some of those samples next. Like content warning, there's a lot of very offensive things. So if you just use this trigger as the prefix, as the prompt to GPT-3 and just ask for continuation, you like immediately get very offensive things that's generally about the black people. And if you prepend this to a neutral context, here the blue part, I love too, is the neutral context, and you still like reliably get the same thing. And similarly for other like neutral context. So you can replace blacks at the end of the trigger with other ethnicities. You can and observe similar effects, although to a lesser degree. So this is highly counterintuitive because the trigger in this case and in the sentiment classification case do not make sense, but they seem to have a high influence on the model. Another work studies these kind of similar, not similar, I guess, also counterintuitive behavior in interpretation methods. So you've probably seen these feature attribution methods that generates a highlight over the input. So here we're looking at a visual question answering example. The question is, what color is the flower in the picture? And the model answers correctly, yellow with high confidence. And then you can generate these highlights and you see, okay, color is highlighted seems reasonable because it's a word that determines like what you should be answering about, right? But does our notion of importance align with what model considers important? So there's a simple test that you can use. You can just only, for example, only keep the important words or remove the unimportant words. So here you see, if we only keep color question mark, the models can still answer yellow correctly, but with a lower confidence. This seems like a very reasonable behavior, right? But there's also like a way we call input reduction that can reduce, iteratively reduce the unimportant words, and it might give you something like this. So just flower question mark, and the model still answers yellow with even higher confidence than if you had color question mark. So these interpretation methods are also behaving weirdly. So with both issues in the model and issues in these explanation methods, it seems like we're not speaking the same language as our models. And this is kind of painting like a worrying picture. But more recently, I've been taking like a more optimistic approach or a pragmatic approach. So I care less about what counts as a good explanation, but more whether these explanations can help humans do things. So the typical way of using these explanations in a deployed system, you'd have a model trained in some feedback loop, typically to emulate human intelligence. So for example, doing visual question answering. And then you add human sort of as a post-processing step, right? This plus sign represents explanation methods that you want to use, line, shape, or like gradient based. But as I said, human is largely a post-processing step, right? There's no the model lives in the feedback loop itself, but the human and the explanation methods are outside that loop. So what I'm advocating here in this talk is we treat human and AI as a learning system and update that in a feedback loop. So contrasting these two paradigms, we can think about what kind of data we can collect. On the left, we obviously have supervised learning. You can collect annotation from humans of doing these tasks as if they're doing it autonomously. you can optionally also have rationale data. So you can ask human to label, provide explanations for either just input or an input and a label. And there are various signals that can inform this sort of interpretability prior. So what kind of information is generally considered explanative or like explaining? But one type of data that you can collect in the paradigm on the right-hand side is how human reacts to different machine explanations. So you show explanations to humans and see what kind of decisions they make. And this allows you to basically optimize your explanations such that human makes certain decisions or they make decisions that satisfies certain properties. But like, why haven't we done this? Of course, this opens up new challenges. And I think there are two main challenges. The first thing is, how do you set up the feedback loop, right? There's not all tasks can generate useful data in this paradigm. So for tasks that humans are perfectly capable of doing themselves, the decision they make with machine assistant can collapse into the decision they make without. So we need to set up the feedback loop and maintain the feedback loop. So this should be something that the human is willing to engage with. And also what kind of update, right? When you get a signal from the learning environment about the effectiveness of a piece of explanation, how do you change the explanation given that update? So I'll pause for a second for questions. Cool. So we believe that we found a very good test bed for setting up this kind of feedback loop and doing adaptive explanations. This is a task called Quizbowl. So Quizbowl is a trivia question answering game that people actually play in real life. Each question in Quizbowl is organized in, sorry, I should first say, Quizbowl is a game played by two teams and there's a judge. The judge will read out the question, and clues in the question is ordered by difficulty. So you start with the most difficult, most obscure clues, and then move on to easier ones. So to give you a bit of taste, one example could start with, this model architecture achieves 41.8 blue score on WMT 14 English French task. Many models using this architecture are named after Sesame Street characters. And finally, this architecture is known for only using attention mechanisms. So in Quizbowl, yeah, go ahead.
Yeah, it's burnt.
Yeah, that's correct. And you probably already knew the answer like before the third clue, right? And yeah, and Quizbowl has this mechanism for you to show that you know more about this topic than other people. So, which is, each player has access to a buzzer. In-person game is a physical device on the table that you can press to signal that you know the answer. And in the middle of the question, you can buzz in and interrupt and provide an answer. If your answer is correct, you get 10 points. If your answer is wrong, you lose some point, and then you are not allowed to try again on this question. So the goal in Quizbowl is to answer correctly and with as little information as possible. So there's accuracy and then there's efficiency in terms of how much information you need. So this is a task. What does our human AI team setup look like? We have judge and a question that kind of describes the environment that the team is updated in. you have a human, and you have some model that's also trying to guess the answer, and we use several explanation methods to glue these two teammates into a team. The human is still in control of the buzzer, so the model's role is just to provide assistance. This team sends its decision to the judge, so whether to buzz and provide an answer or to wait, and the judge will judge the correctness of the answer, and the team receives a score. So some properties that make Quizbowl a good testbed for setting up the feedback loop that I was talking about. First, it has very clear objectives. The scoring is very clear. And there's incentives for the human player to be engaged with the AI and the explanations. So we have reason to believe that these two distributions will not collapse into one. So first, these models are really good. They are on par with not necessarily the best experts, but they are very good. And they also seem to have complementary strengths. We have done adversarial data collection against these Quizbowl models, and we saw that they are not as good as humans at high-level reasoning. So if there's subtle language cues in a question, they are not able to recognize that. But obviously, they are much better at retrieving facts, and they have access to a large collection of previous Quizbowl questions. So to actually collect data, we built this interface. This interface is modeled after some online platform that people use to practice Quizbowl. In the middle, we have the question, which is displayed word by word, similar to how a Quizbowl question is read out in in-person games. On the top, we have a countdown and a button that the players can press and interrupt the question. And then once the player presses the button, there will be a text box for the player to enter. And there will be, I think, 7 seconds for the players to answer, to provide an answer. So the unlike in like regular Quizbowl games, the teammate of each player is a model. So we call this model a guesser, which guesses the answer to the question given this prefix of question that has been displayed. So this model guess will keep updating. So it updates about every 4 words, and it might change over the course of the question. On the left, we have the first form of explanation. So we show not only the top guess, but also the top 5 guesses and the associated score from the model. So it's a confidence score. So you can sort of see this as providing information about the model's uncertainty in its answers. Another signal that people can get from this explanation is whether the model is kind of fluctuating between 2 options, or whether the model is converging on one top answer. We also have what we call evidence. This is a form of example-based explanation. We just retrieve similar looking training examples that are of the same guess. So the model is currently guessing Milton Friedman. These evidence are snippets from previous Quizbowl questions and Wikipedia pages that are about Milton Friedman. And finally, we have highlights. So this is just using a gradient-based explanation method to find the most important words in the question. So these are first generated for the input, the question, and then we find those occurrences of those words in the evidence and highlight those as well. each of these components can be turned on and off independently. So the user can see alternatives but without highlights, or the user can see evidence with highlights but without alternatives. So in the previous work, we did a randomized controlled trial. So each user will randomly see a combination of explanations for each question that they answer. And we collect a bunch of data from that, and we run a regression analysis to isolate the contribution of each explanation. So we experimented with both Quizbowl experts on the bottom. So those are people who are enthusiastic about trivia, and we recruited them from an online forum. We also have crowd workers that we consider novices. And their like average performance indeed confirm that they are much worse than experts. So here we are visualizing the effect as estimated from the regression analysis of each individual explanations. So first, you might notice the effectiveness of different explanations vary across individuals. So for novices on the top, it seems like evidence is more useful. So retrieving relevant training example seems to be more effective at improving their Quizbowl score. But for experts, highlights seems more useful. And then we can also combine these explanations, right? So when we show alternatives and highlights together, we actually see a boost. So you can read this graph as kind of moving the bar from alternatives and stacking that with the bar from highlights. But in the regression analysis, we see the coefficient of this combination is actually larger than the sum of those individuals, which means hypothetically combining these explanations provide extra information to the experts. And this is generally true for experts whenever you combine multiple forms of explanations. But the effect is less positive for novices. And one hypothesis that we had was that novices, so novices generally have less of a time pressure when they play against each other. So they have more time to process the evidence, which might be difficult for experts, but they are overall overly reliant on these explanations. When they see very colorful visualizations on the interface, when they see a lot of information, they tend to think maybe the model is doing something reasonable and tend to agree. We have some evidence to support this hypothesis. This is visualizing the distribution of position where people buzz. So on the left-hand side means you're buzzing at the very beginning of the question. On the right-hand side, you have basically buzzing at the end of the question. This is representing examples, the subset of examples where the model is wrong. So the user, if the user is doing the right thing, the user should reject the model and either wait or provide a different answer. But as you can see, with highlight turned on, the distribution shifts toward the left. So they lose point for being more aggressive when highlight is enabled. And we see basically the same trend across the board for all explanation formats. So some takeaways from this first set of experiments, explanations are not equally effective and they are not additive. So adding more explanation does not mean better. The effectiveness depends on many factors, such as human expertise, and even more fine-grained human expertise. So some people are really good at science quizable questions, some people are good at history. They benefit from different types of explanations. So we should choose explanations adaptively. I'll pause here for questions before I go into the next set of experiments. All right, cool. So this gives us a inspiration for how to incorporate feedback. So as I mentioned, the interface is modular, so you can come up with many different configurations by turning on and off each component. And this could be a way to update, right? You just choose a configuration from the set of possible options and try to find the configuration that works best for each user on each type of question. So the setup looks like the following. We first have a guesser that learned to answer questions autonomously. We have some off-the-shelf explanation methods. So we used feature attribution and example attribution and the form of uncertainty estimate. So to incorporate feedback, we basically update which explanation to show. So we have this model called a selector that chooses explanation configurations for human. And this selector, unlike the guesser, is learned through interaction in games. So the selector's job is pretty simple. Given a representation of the question, so we used word representation, given a set of features about the player, so things like the player's average accuracy, and also the player's average accuracy in different categories of questions, how aggressive the player is buzzing, so the average buzzing position, and the configuration. So I think we had in total 18 different configurations. And the selector basically predicts, okay, for this question and this player, if I show this configuration, what score can this player get on this question? So our method had two phases. We first have a offline pre-training phase where we just take the question, the player, and try to guess what the player scored on that question. So this was trained on a data set collected from older experiments. And then we have this online optimization part that's actively choosing configurations for each question, getting the player to play with that configuration, observe the score, and doing online updates. So there's a trade-off between exploration and exploitation. So you want to try different configurations for each player on different kind of questions and observe how they're performing. But you also want to kind of stick to the configuration that has been proven to work. So it's natural to model this trade-off using Bandit. We use lean UCB, a quite simple Bandit algorithm, but we selected linear UCB and some hyperparameters by simulating different players from the previous experiment. So we will hand code players that perform better with, for example, feature attribution. We had different kinds of simulated players, and we chose this algorithm and hyperparameters from that. But during actual online update, the selector has no knowledge about people's preferences for different configurations. So for example, it did not see the data during actual online optimization, it did not see the data from the previous experiment. So it cannot initialize from like a good ranking of those explanation methods. So there's a concern that by optimizing these explanations, we are kind of taking away agency from human players, right? One way that you could play is basically to act as a buzzer. So you just decide when you're comfortable with the model's prediction, you just buzz there and provide the answer that the model is guessing. And this is indeed the strategy that many people take, especially novices in the previous experiment. So to kind of isolate the effect of explanations in encouraging humans to be better buzzers from all the other possible more interesting effects that explanations might have on humans, we introduced this new condition we call autopilot. So this autopilot is basically a model buzzer. So given all the information that the human knows about the model, so all the same features, um, things like how many words are being highlighted, the performance of this player on the previous data, we train a model to predict whether basically decide whether the human should buzz. So the autopilot basically means the model is thinking for itself. And we change the font color to indicate this. The guess will turn red when the model thinks that it should buzz, and it will stay black when it thinks it should wait for more information. So you can think of this as a approximation of a optimal first order buzzer. So it's only thinking about its own answer. It's ignoring how the opponent is performing. So if we see improvement on top of autopilot condition, that means presumably there is some interesting information that these explanations are providing that's beyond simply a sort of an uncertainty estimate. So does this selective explanation help? Because we're doing an online update, we evaluate cumulative reward. So on the x-axis, we have the number of questions. So equivalently, number of interactions that the selector had with a human. The range is about 150 questions. So we chose this number because from simulation, it seems like the bandit algorithm will need this number of questions to adapt to each user. We commission a new set of Quizbowl questions that no one has seen before, because these trivia experts are very good at memorizing past questions. And on the y-axis, we have a cumulative score from Quizbowl. We have this set of conditions. First, we have a selective explanation. So the model is trying to adapt. We have a condition which is showing everything for all the questions. It's not the best like fixed condition from the previous experiment, but it's very close. We thought it was easier to justify, so we just showed that. We have the condition of auto, and we'll see the model's guess turning red, turning black. And if a human is willing and able to just blindly follow the suggestion of autopilot, basically buzzing when the font turns red, the human should be able to get as good as AI. There's the random condition, which is showing a random configuration for each question. So you can sort of imagine that this can be confusing because the interface is changing and not necessarily in a way that's preferable to each player. We skipped the non-condition, which is just having people play without any assistance, because we recruited experts, and for them, the main motivation is fun. So we want to keep this game kind of fun and fair for them. And finally, you have the AI only baseline. So this is what it looks like, and I'll unpack this. So on top, we have the selective explanation conditions. So indeed, this gives you the best performance for human AI teams. Contrast this with the second best condition, which is showing everything all the time. This kind of validates our hypotheses that you want to be selective, right? You don't want to show everything for all questions. And then this is the autopilot condition. So surprisingly, it's actually worse than showing everything. We don't have like a good explanation for this. Maybe the red and black changing color is not too obvious, and it's actually kind of difficult.
Sorry, just to make sure I understand here. What
Yeah.
you're saying is when the autopilot is signaling, hey, you should weigh in now, that's the red line. And then the kind of yellow green line is not saying that. It's just right. It's just
Yeah.
sorry, that's AI. Yeah. But the
Yeah.
everything fixed is just showing everything, right?
Right.
Right. And these are just experts, right?
These are just experts.
Did you do this also with novices?
Yeah. We saw similar effects with novices, but the gap is smaller.
My guess was going to be that novices are more trusting, and the experts are just kind of looking for the clue they need, but that doesn't bear out from what you're saying.
Yeah, I think that's true. And we novices rarely overrule the model's guess.
Right.
Yeah, so it kind of makes sense that autopilot is more useful for them.
Yeah.
And this line is showing random, so kind of expected. It's worse than having like a static interface, and obviously worse than having an adaptive interface. And finally, this is better than AI only. So this is kind of impressive because if you only look at raw accuracy, this AI is really good. So it's if you only look at accuracy at the end of a question, this AI is better than most human experts, including the ones that we recruited. Specifically, if we like recalling the previous figure of distribution of buzzes, if we focus on questions that the model is making a mistake, can these explanations help experts reject incorrect model predictions? So these are different conditions. Y-axis is percentage of rejection. So you want this to be, sorry, this is a percentage of failing to reject. So you lower is better. So rightmost is AI. It always agrees with its own prediction. So it's 100%. So it's the worst. And none. So the second to the right column is it's the best out of the rest, and it kind of makes sense, right? Because the model is not trying to persuade the human of its own prediction. The positive signal that we take from this.
In the none case, does the human even know what the AI's prediction is?
Yes, it always sees the prediction, but not explanation.
Doesn't see any explanation.
So the positive thing that we take from this is that under the selective condition, the human were able to reject incorrect model predictions more frequently. So some takeaways. We show that you can use selective explanations as a very simple and albeit limited form of adaptive explanation. And you can formulate this problem as contextual bandit, and at least in this specific setup, online optimization was feasible, and we were indeed able to observe improvements. And showing a lot of explanations, there is always the concern of, is it all really explaining or is it trying to persuade? There's the concern of taking agency away from humans, but selectivity, at least empirically, kind of alleviates that concern. I'll pause for a moment for questions.
Just to be clear, so the AI only, of course, has to be 100% because it's just the AI, right?
Sorry, say that again?
The AI only has to be 100% because the AI is doing the predicting.
Right,
So
yeah, exactly.
It's like the same human mistake, right? And so autopilot is better. Is that telling us something than selective, or is that also just a kind of an issue based on just because of the configuration?
Right, yeah, I interpret that as like autopilot probably is not an effective visualization to signal uncertainty. So I sort of interpret that as autopilot being closer to none. rather than like autopilot being better than selective.
Oh, so you're thinking that the humans are just not paying attention to
Yeah,
them.
that was my guess.
Okay, so selective and everything are both pretty good on the previous graph, but selective has fewer rejection of incorrect prediction, which shows that. I mean, but selective is also showing less evidence, so it could be you have the selective case where it decides not to show anything, and then like, well, okay, I'm not going to pay attention.
Yeah, I think there's definitely. So I guess I should clarify that once you select a configuration for the question, that configuration is the same throughout the question. So selective cannot kind of reduce the autopilot by, for example, like showing nothing at the beginning and suddenly showing a lot of explanations in the middle. I'll talk about like extension to that, but
So would you similarly say that random is better than everything because like the user may just not trust the random because it's random?
yeah, I think that was my hypothesis as well. So I should also clarify. So all the users had a reasonable period where they can interact with the system and turn on and off each component by themselves. And we want that process to kind of familiarize the users with this interface. So presumably they formed an opinion about each explanation beforehand, but random will still appear quite unpredictable, I would say. Cool. I want to talk a little bit about why Quizbowl is an interesting architect for a lot of more real-world decision-making problems that we might be interested in. So in Quizbowl, you have a iterative process where the world gives you clues. And at each time step, you need to make a decision of whether I have enough information to make a decision. Right. So in Quizbowl, this is manifested in the decision of buzzing or waiting. This might remind you of medical tests, right? So test conducted on a patient is the world. The world is giving you signals as a doctor, and you need to make a decision whether you need to acquire more tests or if you're ready to make a diagnosis. So because there's a trade-off between maximizing accuracy, so maximizing the correctness of your guess or the quality of your diagnosis, but there's also we also want to minimize cost. So I think having this trade-off opens up opportunities for human AI cooperation, because if we only care about accuracy, in many of these tasks, the AI will be better. Some other points that I wanted to mention. Selective explanation, at least in its current form, has a very limited action space. So our selector policy is only to allow to make one decision for each question. You can imagine a more flexible setting. For example, you're allowed to change the configuration of the interface in the middle of the question. It could be additive, so you could the policy might be allowed to turn on each component at some point in the question. So at the beginning, well, you'll see nothing. Maybe after turn words, you start to show evidence. After turning words, you start to show highlight. So that seems more flexible, and that seems like one step towards like a more realistic setting. We chose this very limited setting because we want to control for sample complexity. Our first priority is to show that this lead to some improvement for experts. Yeah, and eventually you can imagine like extrapolating this action space all the way towards generating sentences. So the sequence of actions will be just a sequence of words. in a sense, this can be seen as a method to increase model self-awareness, because these are post-hoc explanation methods. In the like the traditional way of using these methods, the model is not really aware how it's represented to humans, and the model is also not aware how humans interpret those representations. So by feeding this signal back into the model, or like the whole system becomes kind of self-aware. But I don't like the word self because, for example, here we're updating the explanation part. There's no update happening inside the model. It's kind of hard to say like what counts as the self here. There's a connection between this and pragmatic inference. At the very beginning, I mentioned that I advocate for a more pragmatic approach to interpretability. But you can kind of find a mapping between this and the linguistic sense of pragmatic inference. Just connecting this to other things that you might have thought about. Opponent modeling could be seen as a form of pragmatic inference. Actually, in Quizbowl, there's an older paper from my group that did opponent modeling. So trying to, based on past questions in this game, try to infer whether like the strengths and weaknesses of your opponent. This is something that is very prominent in actual competitive Quizbowl games. You need to sort of gauge your confidence of whether your opponent might buzz. And if you're confident that they will make a mistake, then the optimal strategy is to wait for them to make a mistake and then answer. There's connection to learning general preference. So people might have a preference for different explanations outside the context of this specific decision-making problem. For example, some people might just like highlights, right? I think learning that preference will help a lot as well. There's some connection between this approach to the iterative amplification approach that OpenAI uses in their learning to summarize from human feedback paper. Imagine like collecting augmented human decisions and using that as supervision for the model. So basically, you can distill the team into the next iteration of model, and then you can augment that model with human, and then basically repeat this process. I think my framing emphasis a different aspect of this process. I care more about augmenting human decisions, that the team will make better decisions. I think in their view, this process will converge into a single model, but I'm interested in problems where the human's role is indispensable. So I think I'll conclude here. This, like the main experiment that I talked about here is in this paper called Learning to Explain Selectively. It's a paper by me and Jordan at EMLP, but the content of this talk is inspired by my discussion and my collaborators. And I'll plug an ad, so check out my group's Twitter for latest work on this direction. And we also had a tutorial on evaluations that you might find interesting. All right, thanks so much.
Thank you, Shi, for the great talk.
Thank you.
We'll open now the floor for questions from the audience. You can either ask your questions directly or post them on the chat, and we'll ask them on your behalf.
Awesome.
I was wondering if you have any future work directions that you are planning to work on.
Mm-hmm. Yeah, so opening up the action space is something that we want to work on. We are also interested in different kinds of decision support. So here we showed like feature attribution, example attribution, and turning those on and off. There's a project that we're working on with radiologists where we try to update which example is selected in those example attributions and try to optimize their decision accuracy. I'm also interested in working on settings where you don't get immediate feedback. So here, once you answer a question, you get an immediate score on how you did. I'm interested in like settings where you don't get that immediate feedback. Maybe after a while you get that. So one task that we're considering is learning. So if a human is trying to memorize vocabulary, which word do you pick from, for example, a deck of flashcards for them to practice to maximize the number of new words they memorize over a period of time? Yeah.
Sounds interesting. Any questions from the audience? Okay, if we don't have any questions, I would like to thank the speaker for his time and for joining us today. And yeah, so happy Thanksgiving break, and we will see you in the next NL seminar in 2 weeks.
All right. Thank you so much,
everyone. Teacher, can you please stop the recording? Teacher, can you stop the recording, please?